The strangest shield on Earth is not made of metal or concrete or glass. It has no wall you can touch, no edge you can stand beside, no border guard, no warning sign, no visible surface where safety ends and danger begins. It surrounds the planet like an invisible weather system, always changing shape, always trembling under pressure, always taking the first impact from something the sun is throwing at us. Most days we never think about it. We wake up under blue sky, we check the time on a phone, we follow a map drawn by satellites, we send messages through networks that cross oceans and atmospheres. We trust aircraft to know where they are. We trust power grids to remain steady. We trust spacecraft to keep speaking to Earth. We trust that the sun, a star large enough to swallow our planet more than 1,000,000 times over, will remain politely distant. But the sun is not polite. Every second it releases a wind of charged particles into space. Electrons, protons, streams of plasma that move outward through the solar system, carrying magnetic fields with them. This wind is usually gentle only by cosmic standards. It is not gentle because it is weak. It is gentle because the Earth has something in the way. That something is the magnetosphere, a vast magnetic cavity, a planetary force field, a region of space carved out by Earth's magnetic field, stretched and bent by the solar wind, compressed on the day side, drawn into a long tail on the night side, shaped by forces that are invisible until they collide with air and glow as aurora. On May 19, 2026, a spacecraft called SMILE launched from Europe's spaceport in French Guiana on a Vega C rocket. SMILE is short for Solar Wind Magnetosphere Ionosphere Link Explorer. It is a joint mission between the European Space Agency and the Chinese Academy of Sciences. Its job is not to land on a distant world. It is not to fly past a comet. It is not to look outward into the deep universe. It is being sent to watch the shield around the planet we already live on. And that is why tonight on Dark Matter Radio, we are not beginning with a strange object in deep space. We are beginning with the space just above us, the space that seems empty because our eyes are too crude to see what is happening there. The Earth is not sitting quietly in the sunlight. It is moving through a stream. The sun is breathing. The planet is resisting. Between them is a boundary that changes every minute. SMILE was built to watch that boundary move for most of human history. The sky above the weather felt like a region of silence. There was wind below the clouds, lightning inside storms, rain falling from vapor, snow gathering on mountains, but beyond that there seemed to be stillness. The stars were fixed, the moon came and went, planets wandered slowly, the sun rose and set with the indifference of a clock. Then people began seeing the night sky burn. Auroras have always been beautiful, but beauty can hide violence. A green curtain over the Arctic is not just light. It is evidence that charged particles have entered the upper atmosphere along magnetic field lines. It is the visible trace of an invisible negotiation between Earth and the sun. Oxygen atoms glow green and red. Nitrogen can glow blue, purple, and crimson. The sky becomes a screen for a collision that began millions of kilometers away. It is tempting to imagine auroras as decoration, nature painting the poles, a harmless spectacle for travelers and cameras. But auroras are also warnings. They tell us that the magnetosphere is being disturbed. They tell us that energy has entered the near-Earth environment. They tell us that currents are flowing through space, through the ionosphere, and sometimes through the ground. They are the beautiful edge of a system that can, under the wrong conditions, interfere with the machines that hold modern life together. The Earth's shield begins deep below our feet, not in the atmosphere, not in orbit, not in the cold above the clouds. It begins in the planet's core, in a place no human being can visit and no probe can survive. At the center of Earth is a solid inner core, mostly iron and nickel, surrounded by an outer core of liquid metal. That outer core moves. It convects, twists, and circulates as heat leaves the deep interior. Because the fluid conducts electricity, and because the rotating planet organizes that motion, electric currents arise. Those currents generate magnetic fields. The magnetic fields influence the currents. The whole thing becomes a self-sustaining dynamo, a planet-sized generator. This does not make Earth into a perfect bar magnet. The magnetic field is irregular. It drifts. It weakens and strengthens. Its poles wander. Over geological time it can even reverse. But for now, the field reaches outward from the planet and creates the first condition for life as we know it to remain exposed beneath a relatively stable atmosphere. Without that field, the solar wind would interact with Earth very differently. Mars is the warning written next door. Mars once had a stronger global magnetic field. Today, it has no global magnetosphere like Earth's. It has patchy crustal fields, thin atmosphere, and evidence that solar wind helped strip away much of what Mars once held. The story is complicated. Planetary mass matters, gravity matters, volcanism matters, distance from the sun matters. But magnetic shielding is part of the reason Earth and Mars became such different worlds. We live at the bottom of an ocean of air, and above that ocean is a magnetic ocean. We almost never notice either until something disturbs them. The magnetosphere is not a bubble with a neat skin. It is more like a living shape made by opposing flows. On one side is Earth's magnetic pressure. On the other is the pressure of the solar wind. The day-side magnetosphere is squeezed toward Earth. The boundary where the solar wind first feels the obstacle is called the bow shock because it behaves a little like the shock wave ahead of a boat cutting through water. Behind that is the magnetosheath, a turbulent region where the solar wind has been slowed and heated. Deeper in is the magnetopause, the boundary between solar wind plasma and Earth-dominated magnetic space. On the night side, away from the sun, the magnetosphere is pulled into a long magnetotail. That tail can extend far beyond the orbit of the moon. It is not a tail like smoke. It is a stretched magnetic structure, full of stored energy and plasma, capable of snapping and reconnecting in ways that send particles racing back toward Earth. This is where the shield becomes stranger than the word shield suggests. A shield sounds passive. It sounds like a wall that takes impact. Earth's magnetosphere is not passive. It absorbs energy. It stores energy. It releases energy. It leaks. It reconnects. It channels charged particles into polar regions. It creates radiation belts. It swells and collapses. It rings like a struck instrument. It does not simply block the sun. It interacts with the sun. That interaction is space weather. Space weather is one of those phrases that sounds almost cute until you understand what it means. It does not mean rain between planets. It does not mean clouds in orbit. It means changing conditions in the space environment driven mostly by the sun, solar wind, coronal mass ejections, solar flares, energetic particles, magnetic storms, radiation storms, radio blackouts, conditions that can affect satellites, astronauts, power systems, navigation, and communication. The surface weather can ruin a picnic. Space weather can confuse a satellite, expose a spacecraft to radiation, push electric currents through power lines, degrade GPS accuracy, interrupt radio communication, increase drag on low Earth orbit satellites, and make the sky glow over cities that never expect to see auroras. And yet, for something so important, the magnetosphere has always been difficult to see. We can measure it from within. We can fly spacecraft through it and record particles, fields, and waves. We can place instruments at different locations and reconstruct what happened. We can look at auroras from above. We can build models. We can infer boundaries. But to watch the global magnetosphere change shape as a storm unfolds has been much harder. Imagine trying to understand the weather on Earth with only a few weather balloons drifting through storms and no satellite images of cloud systems. You would know temperature here, wind speed there, pressure somewhere else. You might infer the presence of a cyclone, but you would not see the whole spiral forming over the ocean. SMILE is important because it attempts something closer to a global view. The mission carries instruments designed to observe the interaction between solar wind and Earth's magnetic environment. A soft X-ray imager will look for X-rays produced when highly charged ions from the solar wind interact with neutral atoms in Earth's exosphere, the very thin outermost fringe of atmosphere. An ultraviolet imager will watch auroras. Other instruments will measure magnetic fields and solar wind ions directly. The point is not just to take pretty pictures. It is to connect cause and effect. What did the solar wind do? How did the magnetopause respond? Where did energy enter? How did the aurora change? How did the invisible boundary move? These are not separate questions. They are one system viewed through different windows. This is why SMILE's name is more than a convenient acronym. It is watching the link between the solar wind, the magnetosphere, and the ionosphere. The ionosphere is a region of Earth's upper atmosphere where solar radiation has stripped electrons from atoms and molecules, creating a partially ionized layer. It matters because radio waves interact with it. GPS signals pass through it. Electric currents flow through it. Auroras light within it. The magnetosphere is not out there, disconnected from us. It touches the systems we use. A disturbance that begins as magnetic tension in space can become a current in the ionosphere. That current can induce currents in the ground. Those currents can enter long conductors like power transmission lines or pipelines. A magnetic storm can therefore become an engineering problem. It can reach a transformer without ever touching the air around it. This is the unsettling part. Modern civilization was built during a quiet misunderstanding. We treated space as a vacuum. We treated the sun as a light bulb. We treated the planet's magnetic field as a compass feature. Then we wrapped the world in conductors, satellites, navigation systems, radio links, pipelines, data networks, and power grids. We made civilization electrically sensitive. The sun did not change because we did that, we changed. The best-known warning came in 1859. Richard Carrington, an English astronomer, was observing sunspots when he saw an intense white light flare on the sun. Not long after, Earth experienced one of the strongest geomagnetic storms in recorded history. Auroras appeared at unusually low latitudes. Telegraph systems were disrupted. Some operators received shocks. Equipment sparked. In some reports, telegraph lines worked with their batteries disconnected, powered by currents induced by the storm itself. This was the Carrington Event. It happened in a world where the most vulnerable global technology was the telegraph. There were no communication satellites, no GPS constellations, no electric grids spanning continents, no internet backbone, no astronauts in orbit, no financial systems depending on nanosecond timing from space, no fleets of spacecraft threaded through low Earth orbit. The Carrington Event was terrifying in miniature because the world was still electrically young. A comparable event today would not simply make strange lights in the sky, it would test the assumptions under which the modern world was built. It would test how hardened satellites really are. It would test how prepared grid operators are for geomagnetically induced currents. It would test aviation communication near polar routes. It would test navigation. It would test the difference between a resilient technological civilization and one that only works in fair weather. But the Carrington Event is not the only warning. In March 1989, a geomagnetic storm struck Earth and helped trigger the collapse of the Hydro-Quebec power grid. The blackout lasted about 9 hours. Millions of people lost power. The storm caused problems for satellites and communication systems as well. This was not ancient history. This was the age of computers, spacecraft, and modern power infrastructure, though still less dependent on satellites than we are now. The lesson was simple and uncomfortable. A storm that begins on the sun can turn off lights on Earth, not because sunlight becomes too bright, not because heat arrives like fire, because magnetism changes, because electric currents are induced, because a planetary shield does not merely protect. It transmits stress through a vast system that includes the planet, the atmosphere, the ionosphere, orbit, the ground, and the machines we have built. The first time you really understand that, the world feels less solid. You can look at a city at night and see towers, roads, traffic, screens, aircraft, and power lines. It looks like human design has conquered darkness. But above it all, far beyond the city lights, is a magnetic structure absorbing the mood of a star. If that structure is compressed hard enough, if energy couples into the right regions, if currents flow through the right networks, the city's confidence can become fragile. A grid is not separate from the sky. A satellite is not separate from the sun. The phone finding its location is not separate from plasma. This is why watching the magnetosphere matters. Forecasting space weather is difficult because the sun is complicated and the Earth's response is complicated. A coronal mass ejection can leave the sun and travel across interplanetary space. But whether it produces a severe geomagnetic storm depends on details. Speed matters. Density matters. The embedded magnetic field matters. Especially important is the direction of that magnetic field when it reaches Earth. If the solar wind's magnetic field points southward relative to Earth's field, magnetic reconnection can more efficiently allow energy into the magnetosphere. A huge eruption can miss Earth entirely. A smaller one can arrive with a magnetic orientation that couples strongly. A forecast can know something is coming and still struggle to know how hard it will hit until spacecraft upstream measure it. This is like seeing a storm cloud far away but not knowing the structure of the wind inside it until it is close. At Earth, spacecraft positioned near the L1 point, about 1.5 million kilometers toward the Sun, can sample incoming solar wind before it reaches the planet. That gives warning. But for major events, the warning can still be short, and one-point measurement cannot describe everything about the global response. SMILE does not replace upstream monitors. It adds context. It looks back at Earth's magnetic shield from a highly elliptical orbit, giving long views of the dayside magnetosphere and auroral regions. It tries to watch the shape of the shield itself. That is a profound shift. In ordinary life, a shield is judged after impact. Did the bullet penetrate? Did the wall hold? Did the helmet crack? With Earth, we need to understand the shield while it is being struck, because its motion is part of the risk. The shield can protect the lower atmosphere and surface from direct particle bombardment while still allowing space weather effects to disturb technology. Protection is not immunity. That distinction matters for every planet with a magnetic field, and for every world without one. Jupiter has an enormous magnetosphere, so large that if it glowed visibly in our sky from Earth, it would appear larger than the Moon. But Jupiter's magnetic environment is also violent. Its moon Io feeds plasma into it. Radiation belts around Jupiter are intense enough to threaten spacecraft. A magnetic field can shelter, but it can also trap danger. Earth has radiation belts too. The Van Allen belts, discovered in the early space age, are zones of energetic charged particles trapped by Earth's magnetic field. They are not solid rings. They are dynamic regions. They change with solar activity. Satellites must be designed with them in mind. Astronauts passing through them receive additional radiation exposure, though mission profiles are carefully planned. Again, the shield is not a simple wall. It is architecture made of motion. The solar wind itself begins in the Sun's corona, the outer atmosphere of the Sun. The corona is mysteriously hot, far hotter than the visible surface below it, and plasma escapes outward because the Sun's gravity cannot hold everything in. This outflow fills the heliosphere. The vast bubble dominated by the Sun, Earth orbits inside that bubble. Every planet does. The wind carries the interplanetary magnetic field. Because the Sun rotates, this field forms a spiral structure through the solar system. Earth crosses sectors of it. Streams of faster and slower solar wind interact. Coronal holes send high-speed streams. Active regions produce flares and eruptions. The Sun has an approximately 11-year activity cycle, though the details are messy. Near solar maximum, sunspots, flares, and eruptions tend to become more common. A solar flare is a burst of radiation from the Sun's atmosphere. It can affect radio communication quickly because light and X-rays reach Earth in about 8 minutes. A coronal mass ejection is different. It is a vast eruption of magnetized plasma hurled into space. It can take hours to days to reach Earth depending on speed. Solar energetic particles can arrive quickly along magnetic field lines and pose radiation concerns, especially beyond the protection of Earth's atmosphere. These are different hazards with different timelines. The public often compresses them into one phrase, solar storm. That is understandable. But for engineers and scientists, distinctions matter. A radio blackout is not the same as a geomagnetic storm. A radiation storm is not the same as a coronal mass ejection. Auroras are not proof that a catastrophe is happening. Most geomagnetic activity is manageable. The world does not tremble every time the northern lights appear. But rare extremes matter because civilization is built for probabilities. A bridge is not designed only for normal traffic. A coastline is not planned only for calm seas. A power grid cannot be understood only on quiet magnetic days. The problem is that human memory is short, and the Sun's memory is not human. We have detailed satellite-era observations for only a small fraction of the timescale on which extreme solar events occur. We have historical records, ice cores, tree rings, and indirect evidence of past solar particle events. But the modern technological system has not lived through every kind of storm the Sun can produce. It has lived through samples. It has lived through warnings. The shield has been tested. It has not been exhausted. This does not mean panic is useful. Panic almost never understands scale. The magnetosphere is strong, the atmosphere is thick. A solar storm is not going to peel people off the surface or make the oceans boil. Most people on the ground are physically protected from particle radiation by the atmosphere and magnetic field. The danger is not that the sky will fall. The danger is that invisible disturbances can enter invisible dependencies. GPS is a good example. A GPS receiver works by timing signals from satellites. To determine position, it needs extremely accurate timing. Those signals pass through the ionosphere, where free electrons can delay and distort them. During disturbed space weather, ionospheric conditions become more irregular. That can reduce accuracy or cause signal problems. For a person walking in a city, this may be annoying. For aviation, shipping, precision agriculture, surveying, emergency response, and systems that use satellite timing, the stakes can be higher. Radio communication is another example. High-frequency radio can bounce off the ionosphere, allowing communication beyond the horizon. But the ionosphere is not stable glass. It changes with solar radiation, geomagnetic activity, time of day, season, latitude, and storm conditions. During solar flares or geomagnetic disturbances, some radio paths can degrade or fail. Polar routes are especially sensitive because energetic particles can enter near magnetic poles. Satellites face still more direct risk. A satellite is a machine placed in an environment that wants to age it. Charged particles can damage electronics. Radiation can flip bits in memory, degrade solar panels, and interfere with sensors. During geomagnetic storms, the upper atmosphere can heat and expand, increasing drag on satellites in low Earth orbit. More drag means orbits decay faster. Operators may need to adjust positions. Tracking can become more difficult when many objects are affected. There is something strange about calling low Earth orbit space. It is space, but it is not empty. It is within the outer breath of Earth's atmosphere. When solar activity heats that breath, satellites feel it as resistance. Even debris feels it. Space weather can change the motion of objects we are trying to track, and in an era with thousands of satellites and growing orbital congestion, that matters. Astronauts are another concern. In low Earth orbit, astronauts are partially protected by Earth's magnetosphere, though still exposed to more radiation than people on the ground. Beyond low Earth orbit, on missions to the Moon or Mars, radiation becomes a more serious planning problem. Solar particle events can be dangerous if astronauts are not adequately shielded. A future of lunar bases and deep space travel depends not only on rockets and habitats, but on understanding when the Sun is about to become hostile. This connects the magnetosphere to the Moon, to Mars, to the whole human project beyond Earth. If we want to live off-world, we must learn the weather of space as seriously as sailors learned the weather of oceans. The first mariners did not conquer the sea by pretending storms did not exist. They learned patterns. They built instruments. They read clouds, pressure, swells, currents, stars. Spacefaring civilization will need the same humility with plasma and magnetism. SMILE is one instrument in that larger humility. It will not solve space weather by itself. No single spacecraft can, but it can help scientists compare global images with local measurements, improve models, and understand how the magnetosphere responds as a connected system. The invisible shield will not be a metaphor only. It will become a structure with observed motion. That matters because models are only as good as the reality used to test them. A model of the magnetosphere must handle boundaries, reconnection, particle populations, currents, waves, and coupling to the ionosphere. It must describe a system that changes from calm to storm and back again. The mathematics is not simple. Plasma is not simple. Magnetic fields embedded in conductive fluids and charged particles behave in ways that resist everyday intuition. In ordinary experience, we separate matter from fields. A stone is a thing. A breeze is a motion. A magnet pulls metal. But in plasma physics, matter and electromagnetic fields are deeply entangled. Plasma carries currents. Currents create magnetic fields. Magnetic fields guide charged particles. Moving magnetic fields induce electric fields. Energy changes form. Boundaries form without walls. The magnetopause is not a wall. It is an agreement between pressures. Magnetic reconnection is one of the most important processes in that agreement. It occurs when magnetic field lines arranged in opposing directions break and reconnect, releasing energy. Field lines are not physical strings, but they are useful ways of describing magnetic direction. When reconnection happens, magnetic energy can be converted into particle energy and heat. In Earth's magnetosphere, reconnection helps transfer energy from the solar wind into the magnetosphere. In the magnetotail, reconnection can accelerate particles toward Earth and intensify auroras. The phrase field lines breaking is not literally a rope snapping, but the effect can be just as dramatic. A quiet magnetic structure suddenly changes connectivity. Particles that were trapped or guided one way can be sent another way. Energy stored in stretched magnetic fields can be released. The aurora can brighten. Currents can strengthen. Space can become electrically active. This is why a visible aurora is only the lower edge of something larger. When you see green light above a polar landscape, you are seeing atoms in the upper atmosphere emit photons after being excited by incoming particles. But those particles are part of a circuit that extends into space. They are responding to magnetic and electric fields shaped by the solar wind. The light is local, the cause is planetary. The beauty is real, so is the machinery. Ancient people saw auroras and created myths. Some saw spirits, some saw omens, some saw fires beyond the northern horizon. In a way, the myths were not wrong to treat auroras as messages. They are messages, not from gods but from the Sun-Earth system. They tell us the magnetosphere is alive with motion. Modern science changes the content of the message, not the feeling that something immense is speaking in light. SMILE's ultraviolet imager watching auroras is therefore not merely taking images of a spectacle. It is watching the footprint of magnetospheric energy entering the atmosphere. It is reading a glowing signature of invisible physics. The soft X-ray imager adds another kind of vision. Soft X-rays can be produced through solar wind charge exchange. Highly charged ions in the solar wind encounter neutral atoms, capture electrons, and emit X-rays. This makes certain regions around Earth detectable in a way they otherwise would not be. It is a clever trick. Instead of trying to see the magnetosphere directly, SMILE looks for faint emissions produced by interactions at its edges. The shield becomes visible because the solar wind touches it. There is something poetic about that. We cannot see the boundary until it is being struck. The shield reveals itself under pressure. The spacecraft's orbit matters because geometry matters. From the wrong place, the magnetosphere is a local environment. From the right high orbit, it becomes a shape. SMILE's highly elliptical orbit gives it long observing periods from far away, especially over high northern latitudes, allowing the spacecraft to view large-scale structures and connect them with in-situ measurements. A spacecraft looking back at Earth from such a distance does something psychologically important too. It changes the planet from home into object. We are used to seeing images of Earth as a blue marble, fragile and luminous. SMILE asks us to imagine another image layered over that one. Earth surrounded by an invisible, changing magnetic form, facing the sun like a ship facing weather. The blue marble is not unprotected. It is defended by a field generated in darkness deep underground. This defense is not evenly distributed. Magnetic field lines emerge and curve. Near the poles, they provide pathways for charged particles to enter the upper atmosphere more easily. That is why auroras cluster around polar ovals rather than appearing uniformly everywhere. During stronger storms, those ovals can expand toward lower latitudes, bringing auroras to regions where they are rare. When auroras move south, people notice. Cameras fill the internet. The sky turns green over farms, suburbs, deserts, and cities. For many, it feels like a gift. But for space weather forecasters, low-latitude auroras mean the system is disturbed. The same event can be wonder and warning. That duality runs through this entire subject. The sun gives life. The sun threatens technology. The magnetic field protects Earth. The magnetic field channels particles into auroras. The ionosphere enables radio communication. The ionosphere distorts signals. Space is empty enough to orbit through but active enough to damage machines. The shield saves us from one kind of exposure while connecting us to another kind of vulnerability. Nothing is simple when the planet is inside a star's atmosphere. That is another way to say it. Earth is not outside the sun in the way a person outside a house is separate from the house. Earth orbits within the sun's extended influence. The heliosphere reaches far beyond the planets. The solar wind fills interplanetary space. The sun's magnetic field threads through the region where Earth moves. We live inside the outer reach of our star. Night hides this from us. At night, the sun is below the horizon, and it feels absent. But the solar wind does not turn off. The magnetotail stretches away from the sun on the night side. Energy stored there can release after midnight. Auroras can dance when the sun is not visible. The star is still in the room. This is why the magnetosphere can feel slightly unsettling. It reveals that our planet is not isolated. We are embedded, connected, continuously acted upon. Modern civilization likes the idea of control. We build clocks, grids, networks, financial systems, orbital constellations. We make things predictable. We schedule the world. Space weather reminds us that predictability is negotiated with a star. A severe geomagnetic storm does not care about market hours. It does not care about satellite replacement schedules. It does not care that a hospital needs power or that an aircraft needs communication. It is not malicious. It is plasma following physics. That makes it more unsettling, not less. There is no intention behind it. There is only scale. To understand that scale, consider the solar wind as a continuous flow. Even on quiet days, Earth is being struck by particles moving hundreds of kilometers per second. The magnetosphere stands against that flow. The bow shock forms because the solar wind is supersonic relative to the obstacle. It must slow and divert around Earth's magnetic cavity. The pressure balance changes when the solar wind becomes faster, denser, or more magnetically connected. During strong solar activity, the dayside magnetosphere can be compressed inward. Satellites that normally orbit within one region may find themselves exposed to another. Boundaries move. Radiation belts change. The whole near-Earth environment is rearranged. A shield that moves can surprise machines designed around averages. Engineers account for these conditions, but engineering is always a conversation with uncertainty. How often will extreme events occur? How severe can they be? How much redundancy is enough? Which satellites are most vulnerable? Which transformers are at risk? Which regions are geologically more susceptible to geomagnetically induced currents? How much warning is practical? What does society consider an acceptable risk? These are scientific questions and political questions. Space weather is not only about plasma, it is about infrastructure governance. It is about whether warnings reach operators in time. It is about whether power companies invest in mitigation before rare events. It is about whether satellite constellations are designed with resilience or only with cost in mind. It is about international coordination because the sun does not send storms only to one country. The launch of SMILE as a Europe-China mission sits inside that reality. Science can cross political boundaries even when politics becomes difficult. ESA and the Chinese Academy of Sciences working together on a mission to study Earth's magnetic shield is a reminder that some hazards are planetary. The solar wind does not recognize alliances. A geomagnetic storm is not impressed by borders drawn on maps. It couples into the Earth system at scales larger than nations. That does not mean science is outside geopolitics. It never is. Space missions involve technology transfer, export controls, launch systems, funding decisions, prestige, data policy, institutional trust, and strategic caution. A joint mission can be both a scientific achievement and a political signal. The fact that SMILE exists says something about cooperation. The difficulty of such cooperation says something too. There is a subtle irony here. The mission studies the boundary between Earth and the solar wind, while being built across human boundaries that are themselves under pressure. A planetary shield watched by a divided planet. Maybe that is fitting. The magnetosphere is not smooth because the universe is not smooth. Cooperation is not smooth because history is not smooth. Yet the need to understand the environment around Earth remains. Satellites from many nations share orbital regimes. Power grids cross borders. Communication networks interconnect. Aviation routes link continents. Space weather is a common exposure. This is one reason the word shield can mislead us. It sounds like something that belongs to Earth alone, but the consequences of that shield's motion belong to every society that depends on technology. A person in Guwahati, London, Beijing, New York, Montreal, Nairobi, or Sydney may never think about the magnetopause, but they may use a phone guided by satellites, money transferred through systems timed by atomic clocks, weather forecasts informed by spacecraft, flights routed through communication networks, and electricity transmitted across long lines. The magnetosphere is overhead, but its influence is woven into daily life. The invisible has become infrastructural. That may be the deepest theme of this story. Human beings often build around things we cannot see. Gravity is invisible, but architecture obeys it. Air pressure is invisible, but aircraft depend on it. Germs were invisible before microscopes, but human history was shaped by them. Electromagnetic waves are invisible, but modern communication rides on them. The magnetosphere is another invisible condition of civilization. We did not invent it, we inherited it. And now we're beginning to monitor it like infrastructure. There is a difference between discovering a natural phenomenon and becoming dependent on predicting it. Early astronomers studied the sun to understand cycles and spots. Telegraph operators learned the hard way that solar activity could enter wires. Space-age scientists learned that satellites and astronauts must survive radiation environments. Now, as civilization becomes more dependent on orbital systems, space weather prediction becomes not a curiosity, but a public service. NOAA's Space Weather Prediction Center, ESA space weather activities, NASA heliophysics missions, and other national and international efforts all belong to this shift. The magnetosphere is not just a subject for papers. It is part of risk management. But risk management requires imagination. The worst failures often come from treating the past few decades as the full range of possibility. If a grid has not failed recently, it can feel safe. If satellites usually recover from anomalies, operators can feel confident. If auroras are rare at low latitudes, people can treat them as novelties. But the sun is not bound by the length of a human career. A star can be quiet long enough for us to mistake quiet for normal. Then it can remind us. One of the unnerving things about the Carrington Event is not simply that it was powerful. It is that it happened before the world was vulnerable in the ways it is now. The storm revealed a coupling between solar activity and technology at the very beginning of electrical civilization. It was like hearing a floor creak in an empty house before moving in with thousands of glass instruments. We moved in anyway. This does not mean we were foolish. Electricity transformed life. Satellites transformed communication, navigation, science, weather forecasting, disaster response, and global awareness. The answer is not to retreat from technology. The answer is to understand the environment technology lives in. Ships did not stop crossing oceans because storms existed. They became better ships. Power grids, satellites, and space missions must become better ships. SMILE can help by making the shield more observable. It will provide data that scientists can use to study dayside reconnection, magnetopause motion, cusp regions, auroral responses, and solar wind coupling. The cusp regions, near where magnetic field geometry allows solar wind particles easier access into the magnetosphere, are especially important. They are like funnels in the magnetic architecture. Understanding them helps explain how energy enters. These details may sound remote, but every improved understanding can feed models. Better models can support better warnings. Better warnings can support better decisions. A grid operator may not care about the poetry of a magnetotail, but they care if induced currents threaten equipment. A satellite operator may not care about auroral beauty, but they care about radiation and drag. An astronaut may not care about the name of an imager, but they care about sheltering during a particle event. A pilot may not care about plasma turbulence, but they care about communication at high latitudes. Science becomes practical through chains of translation. A soft X-ray photon detected by SMILE becomes a data point. Data points become maps. Maps test models. Models improve forecasts. Forecasts become alerts. Alerts become actions. Actions keep systems alive. The chain is fragile, but it is real. There is another chain too, one that goes backward in time. Earth's magnetic shield has existed in some form for billions of years, though it has changed. Life evolved beneath it. The atmosphere persisted under the combined protection of gravity, magnetic field, chemistry, and distance from the sun. The ocean surface received sunlight filtered by air and ozone. Organisms never needed to understand the magnetosphere to benefit from it. This is common in nature. We live inside protections we do not recognize. A child does not understand the immune system while recovering from a cold. A bird does not understand aerodynamics while flying. A forest does not understand the carbon cycle while growing. Civilization did not understand the magnetosphere while building under it. But understanding changes responsibility. Once you know the shield exists, you cannot treat the space around Earth as empty. You begin to see the planet differently. The ground is no longer the whole world. The atmosphere is no longer the only envelope. The environment includes fields, particles, radiation belts, plasma boundaries, and currents. Earth is a layered system extending far beyond the air. Even the word Earth becomes too small if it means only rock and ocean. Earth includes the magnetic reach of the core. It includes the ionosphere touched by sunlight. It includes the exosphere where atoms are sparse enough to drift far out. It includes the magnetotail streaming away from the sun. It includes the invisible architecture that spacecraft move through and storms reshape. When SMILE looks at the magnetosphere, it is looking at Earth, not the surface Earth, not the map Earth, the larger Earth, the Earth that touches space. This larger Earth is deeply dynamic. It has daily rhythms and storm rhythms. The ionosphere changes between day and night because sunlight ionizes atoms and molecules. The magnetosphere changes with solar wind pressure. The auroral oval shifts. Radiation belts respond to storms. The plasmasphere, a region of cold dense plasma co-rotating with Earth, can erode and refill. Currents flow along magnetic field lines and across the ionosphere. It is a weather system with no clouds. To most listeners, this may feel abstract, so bring it back to something familiar. Think of standing outside before a thunderstorm. The air changes, the light changes, leaves turn their pale undersides to the wind. You may not see the pressure field or the electric charge separation inside clouds, but you feel that the environment has become loaded. Space weather is like that, except the charged environment extends across tens of thousands of kilometers, and the storm source is a star. The problem is that humans do not have senses for it. We can feel wind on skin, we can smell rain, we can hear thunder, but we cannot feel the magnetopause compress. We cannot smell reconnection in the magnetotail. We cannot hear energetic particles striking spacecraft electronics. We need instruments to give the invisible a voice. SMILE is one of those voices. It converts unseen interactions into images and measurements. It gives scientists the chance to watch the shield breathing under solar wind pressure. It helps turn a planetary defense from an abstraction into an observed system. There is an old pattern in science. First, a phenomenon is invisible. Then it becomes detectable. Then it becomes measurable. Then it becomes predictable, though never perfectly. Lightning was once divine anger, then electricity, then atmospheric physics. Disease was once bad air or curse, then microbes, then epidemiology and medicine. Space weather is moving along a similar path. Aurora was wonder, then magnetism, then solar terrestrial physics, now operational forecasting. The shield is entering the age of surveillance. That phrase sounds ominous, but in this context it may be necessary. The planet's magnetic environment is not something we can control. We can only watch, understand, and prepare. There is no switch on the sun. We can shut down vulnerable systems, reconfigure satellites, delay launches, adjust flight routes, protect astronauts, manage grid loads, and issue alerts. But we cannot stop a coronal mass ejection. We cannot command the solar wind to turn aside. We cannot strengthen the geodynamo on demand. We cannot tell magnetic reconnection to wait until Monday. The universe does not ask for permission to be dangerous. This should not make us despair. It should make us precise. Precision is the opposite of panic. A bad understanding says the sun might destroy everything at any moment. A better understanding says severe storms are rare but consequential. Mechanisms differ. Vulnerabilities can be reduced, and prediction improves with observations. A bad understanding says the magnetic field is a magic force field. A better understanding says it is a dynamic system that deflects much solar wind, traps particles, couples energy into the ionosphere, and changes shape under pressure. Dark matter radio exists in that space between wonder and precision. The universe is stranger when described accurately. A fake mystery fades when examined. The real mystery deepens. The magnetosphere is a real mystery, not because we know nothing about it, but because what we know opens further questions. How exactly does energy move across scales, from solar wind flows larger than Earth down to particle acceleration and waves? How do global magnetospheric structures respond to rapidly changing solar wind conditions? How can forecasts better connect upstream solar wind measurements to ground-level impacts? What can Earth teach us about exoplanets orbiting active stars? That last question opens another door. Earth's magnetic shield is not only a local subject, it matters for astrobiology. When scientists think about whether planets around other stars can support life, they consider atmosphere, liquid water, stellar radiation, planetary mass, orbit chemistry, and magnetic fields. Around active red dwarf stars, close-in planets may face intense stellar activity. A magnetic field could help, but the situation is complex. Too weak a field, too thin an atmosphere, too much stellar violence, and a planet may struggle to remain habitable at the surface. Earth becomes a case study in survival near a star. We sometimes imagine habitable planets as blue spheres at the right distance. But habitability is not only distance, it is endurance. Can the atmosphere last? Can radiation be moderated? Can chemistry remain stable long enough for life to emerge and persist? Can a planet protect itself from its star while still receiving the star's light? A habitable world is not just warmed, it is defended. That gives SMILE a broader significance. By studying our own magnetosphere, we improve our understanding of planetary magnetic shields in general. Earth is the only planet where we can study this coupling in such detail with dense technological context. It is our laboratory, our home, and our warning system. There is a hidden humility in that. The more advanced our instruments become, the more they reveal dependence. We are not above nature because we can observe it. We are more aware of how much of our world nature is holding up. The core keeps moving. The field keeps extending. The sun keeps blowing, the shield keeps responding. Under that exchange we build cities and argue about small things. The scale mismatch is almost absurd. A solar eruption larger than Earth occurs on a star 93 million miles away. Its magnetic structure travels through space. It reaches our planet. It compresses a boundary tens of thousands of kilometers above us. Energy enters the magnetosphere. Currents intensify in the ionosphere. Electric fields are induced in the ground. A transformer groans. A satellite resets. A radio link fades. Someone looking up from a dark road sees green light in the sky and thinks it is beautiful. All of that can be one event. This is why science is not only a collection of facts. It is a way of seeing connections where ordinary life sees separate things. The sun and the transformer are connected. The aurora and the GPS error are connected. The core beneath your feet and the solar wind above the atmosphere are connected. A spacecraft named SMILE was launched to watch the connection. Its launch date will eventually become just one line in a mission history, but the idea behind it is larger. It marks another step in treating the near-Earth space environment as something visible, dynamic, and operationally important. It says that the space around Earth is not a blank stage on which satellites move. It is an active medium, and active media have weather. Consider what would happen if humans could suddenly see the magnetic field with naked eyes. The world would feel haunted at first. Lines would arc from pole to pole. Storms from the sun would deform the sky, the night side would trail into a vast tail, auroral ovals would pulse like crowns around the poles. During storms, the whole structure would ripple. We would never again say space is empty. But because we cannot see it, we forget. Human attention is biased toward surfaces. We notice mountains, oceans, buildings, bodies, screens. Fields feel unreal because they do not have edges our hands can find, yet fields are among the most real things in physics. Gravity holds planets. Electromagnetism holds atoms, drives chemistry, carries light, powers machines, and shapes plasma. The invisible is not less physical than the visible. It is often more fundamental. The compass needle is a tiny confession. It admits there is a field passing through the room. You can hold it in your hand and watch it align with something larger than the house, larger than the city, larger than weather. The needle points because Earth's magnetic field is present. The same field reaches into space and forms the shield Smile is watching. The everyday and the cosmic are linked by that little motion. A child playing with a magnet and iron filings is seeing a classroom shadow of the same physics that shapes planetary environments. The filings trace field patterns. Around Earth, charged particles trace more complex magnetic geometries. The scale changes. The equations become harder. The principle remains. The universe writes in invisible lines. Sometimes those lines protect us. Sometimes they guide danger toward the poles. Sometimes they store energy until it is released. This is why the word force field is both useful and misleading. It captures the intuition of an invisible defense, but it sounds too clean, too science-fictional. Earth's magnetosphere is not a perfect dome. It has cusps, tails, belts, currents, plasma sheets, waves, and leaks. It is a shield with doors that open under certain conditions. It is a shield made of relationships. The most important door is magnetic reconnection. When the interplanetary magnetic field carried by the solar wind aligns in a way that opposes Earth's dayside field, reconnection can occur at the magnetopause. Energy and plasma can enter. Later, reconnection in the magnetotail can release stored energy. The aurora brightens. A geomagnetic substorm unfolds. Substorms are not the same as major geomagnetic storms, but they reveal the magnetosphere's habit of storing and releasing energy. The nightside tail stretches, thins, reconnects, and snaps back. Particles rush along field lines. The upper atmosphere glows. It is not hard to see why earlier cultures treated auroras with awe. Even knowing the physics, awe remains appropriate. Explanation does not reduce the sky. It deepens it. Green light is more astonishing when you know it is oxygen responding to particles guided by a planet-wide magnetic structure disturbed by the sun. Knowledge does not kill wonder. It removes cheap wonder and leaves the real thing. The real thing is enough. The Carrington Event remains powerful partly because it was observed at a pivotal moment. Carrington saw the solar flare. Telegraph systems felt the geomagnetic storm. The chain between sun and technology became visible. In a sense, the event was the first rough sketch of modern space weather. The sketch has become more detailed with every decade. The International Geophysical Year helped coordinate observations. The space age placed instruments above the atmosphere. Explorer 1 discovered trapped radiation. Later missions studied solar wind, magnetotails, magnetopause crossings, auroras, particles, and fields. NASA's magnetospheric multiscale mission studied magnetic reconnection with multiple spacecraft flying in formation. Solar missions watched. The sun-ground magnetometer networks recorded disturbances. Supercomputers modeled plasma. SMILE enters a long conversation. Its distinct contribution is global imaging of large-scale structures using soft X-rays and ultraviolet observations. That does not make older missions obsolete. It adds a missing perspective. Local measurements are like microphones placed inside an orchestra. Global imaging is like seeing the conductor and the whole stage. You need both to understand the performance. The magnetosphere is an orchestra with no audience, except we are inside the hall. Most of the time the music is quiet, then the sun strikes a louder note. When that happens, the first alerts may come from solar observatories. The flare erupts. A coronal mass ejection is seen leaving the sun. Models estimate its direction and arrival. Upstream monitors measure the solar wind as it approaches Earth. Space weather centers issue watches or warnings. Operators prepare. Satellites may be put into safer modes. Astronauts may be directed to shelter. Grid operators may monitor currents. Radio users adapt. This is already happening. The question is how much better it can become. Better does not mean perfect. Weather on Earth is still hard, even with dense observations and centuries of study. Space weather has fewer instruments, larger scales, and plasma physics that can be chaotic, but prediction does not need perfection to be valuable. A hurricane forecast with uncertainty can still save lives. A geomagnetic storm forecast with uncertainty can still help protect systems. The hardest part may be getting society to care before the sky turns green. Risk that is invisible most of the time is easy to neglect. Space weather competes with immediate problems. Budgets are finite, infrastructure upgrades are expensive, severe storms are rare, political attention is short. It is always tempting to assume tomorrow will resemble yesterday. The sun is patient with our assumptions. It does not need to punish us often. It only needs to surprise us once in the wrong way. This is where stories matter. A mission like SMILE can be described as 4 instruments in a high orbit studying solar wind magnetosphere-ionosphere coupling. That is accurate. It is also emotionally inert for most people. Another way to say it is this: humanity has launched a spacecraft to watch the invisible shield that keeps our technological world from being more exposed to the moods of the sun. Both sentences are true. The second one lets the mind feel the scale. Dark matter radio lives in that second sentence without betraying the first. We can be precise and still feel the room go colder. There is also a deeper philosophical question underneath the engineering. What does it mean for a civilization to depend on something it did not build and cannot repair? If a bridge fails, we can rebuild it. If a transformer burns out, we can replace it. If a satellite dies, we can launch another, though not instantly. But if Earth's magnetic field weakened dramatically over geological time, or if the geodynamo behaved differently, we would not be able to fix the planet. We are beneficiaries, not maintainers, of the largest protective system we have. Of course, the magnetic field naturally changes over time. Pole drift and field variations are real. Reversals have happened in Earth's history. A reversal does not mean the field disappears entirely overnight, and it is not a doomsday switch, but the fact that the shield is generated by a dynamic planetary interior reminds us that habitability is maintained by processes, not guaranteed by labels. Earth is habitable because many things keep happening. The core keeps convecting. Plate tectonics help cycle carbon over long timescales. The atmosphere maintains pressure and chemistry. The oceans move heat. The moon stabilizes aspects of Earth's rotation. The sun remains stable enough. Life modifies its own environment. Remove or disturb enough of these processes, and a world changes. The magnetosphere is one process among many, but it is a grand one. It is the deep Earth reaching into space. That phrase is worth sitting with. The shield above the atmosphere is generated below the crust. The danger it resists comes from the sun. The effects appear in the upper air, in orbit, in radio systems, and in power lines. The system connects the core, the star, the sky, and the city. There are not many subjects that cross-scale so beautifully. A piece of iron in the core participates indirectly in the survival of a satellite. A charged particle from the sun participates indirectly in a transformer's stress. An aurora over the Arctic participates in a global electrical system. The world is less compartmentalized than our words imply. This is why invisible science often feels mystical, even when it is not mysticism. It restores continuity. It shows that boundaries are sometimes conveniences of perception. The ground is not the end of Earth. The atmosphere is not the end of weather. The horizon is not the end of the sun's influence. SMILE will watch this extended Earth from orbit, but the mission also asks us to watch our own blindness. Why did something so important remain so absent from ordinary thought? Perhaps because the magnetosphere usually works. Successful protection is quiet. A roof is noticed when it leaks. An immune system is noticed when it fails. A magnetic shield is noticed when auroras spread south, satellites misbehave, radios fade, or grids shake. Invisible systems become visible through failure. Science tries to make them visible before failure. That is the noble part of this. To study space weather is to refuse surprise as a governing principle. It is to say that the universe may be vast and violent, but patterns can be known, not conquered, known, enough to prepare, enough to reduce harm, enough to replace superstition with vigilance. There is no shame in being vulnerable to the sun. Every planet is. The question is whether an intelligent species can recognize the terms of its vulnerability. The sun is not an enemy. It is the reason Earth is warm, bright, and alive. But sources of life can also be sources of hazard. Water sustains life and floods cities. Air fills lungs and carries storms. Fire cooks food and burns forests. The sun powers ecosystems and hurls plasma into space. Nature rarely fits into one moral category. The magnetosphere does not make the sun safe, it makes Earth possible. That may be the best way to understand it, not a guarantee. A possibility, the possibility of atmosphere, the possibility of satellites, the possibility of navigation, the possibility of electrical civilization under a star. When we look at auroras, we are seeing the cost of that possibility. Energy entering the system, light produced by particles that found their way down magnetic paths. When we monitor geomagnetic indices, we are measuring the shield's disturbance. When we launch SMILE, we are trying to watch possibility being maintained in real time. The mission's first years will be full of technical details: commissioning, calibration, orbital maneuvers, data validation, instrument performance, scientific papers. The public may hear little unless there is a spectacular image or a strong storm. That is normal. Most serious science enters culture slowly. It builds quietly. But even if SMILE never becomes a household name, the idea it represents should. Earth is not merely protected by distance from the sun, it is protected by a dynamic magnetic environment. That environment can be disturbed. Those disturbances can matter. Watching them is part of living responsibly in a technological age. The first people who saw Earth from the moon described a fragile blue world hanging in darkness. SMILE adds another layer to that image. Around the blue world is a shield that cannot be photographed in ordinary light, shaped by the planet's heart and the star's breath. It is not a halo. It is a struggle, a beautiful struggle, a constant one. There is a temptation in science storytelling to end with reassurance. To say the shield is there, the scientists are watching, and everything will be fine. But that would be too simple. The better ending is more honest. The shield is there. The scientists are watching. Everything is not guaranteed. That is why watching matters. The magnetosphere has defended Earth for longer than human beings have existed. But modern civilization has created new forms of exposure. We have placed delicate machines in orbit. We have stretched conductors across continents. We have made timing from satellites part of the hidden skeleton of daily life. We have become a species whose ordinary routines depend on conditions in near-Earth space. The old shield now protects new fragilities. This is not a reason to fear the sky every morning. It is a reason to understand the sky more completely. Somewhere above us at this moment, the solar wind is flowing around Earth's magnetic field. The bow shock is standing in space. The magnetopause is shifting. The tail is stretching away from the sun. Particles are spiraling along field lines. Currents are moving through the ionosphere. Instruments are measuring. Models are updating. The planet is not still. You are sitting under a moving shield. You have been your entire life. And perhaps the most unsettling thing is that the shield works so well that it lets us forget it exists. SMILE is a reminder. A spacecraft launched by Europe and China, riding a Vega C rocket into the dark, sent not to escape Earth, but to look back at the invisible structure around it, to watch the boundary between the star and the world, to turn the hidden defense of civilization into data. There is humility in that backward gaze. We often look into space to find what is far away: exoplanets, black holes, galaxies, the beginning of time. But sometimes the strange thing is not far away. Sometimes it is the invisible architecture wrapped around home. The Earth is not naked in space. It is shielded but not sealed, protected but not isolated, watched but not controlled. And somewhere beyond the atmosphere, the sun keeps pressing against the field generated in the dark center of the planet, and the field keeps answering. That answer is the reason the sky remains mostly quiet. It is the reason auroras are rare gifts instead of constant fire. It is part of the reason civilization can build beneath a star and call the arrangement normal. But normal is not the same as simple. Normal is a shield we cannot see, a storm we may not feel, a power grid that assumes the sky will behave, a satellite listening through radiation, an astronaut waiting for warnings, a planet carrying its magnetic shadow through the solar wind. Normal is stranger than it looks. So the next time you see the northern lights in a photograph or hear that a solar storm might make auroras visible farther south, do not think only of color. Think of the entire invisible machine: the core, the field, the wind, the boundary, the particles, the currents, the satellites, the wires, the people watching. Think of a shield that glows only when it is disturbed. Think of a civilization asleep beneath it. And think of a small spacecraft named SMILE, far above Earth, trying to see the thing that has been saving us quietly all along. What this episode reveals is not that Earth is safe in any absolute sense. It reveals something more delicate. We live inside protection that is dynamic, imperfect, and deeply physical. We are not separated from the sun by emptiness. We are separated from its charged wind by a magnetic structure born in the planet's core, shaped by plasma and watched now by instruments that can translate invisible pressure into knowledge. The open question is how well a technological civilization can learn to live with a star, not worship it, not fear it blindly, not pretend it is just a lamp in the sky. Live with it, watch it, understand its warnings, build systems that remember the sky is active even when it looks calm. Maybe that is what maturity means for a spacefaring species, not leaving Earth behind but finally seeing the Earth completely, the rock, the air, the ocean, the field, the shield. Subscribe to Dark Matter Radio, and if this leaves you with a question, leave it in the comments. Maybe your question is about the sun, maybe it is about auroras. Maybe it is about how much of modern life is quietly balanced on forces we never learned to notice. Until next time, keep listening to the dark.